that image geometry is by following the Corearchy condition equation. So you already know that. But right now, pretend that you don't know. Right? Pretend that you don't know. And right now, what you want to do is you want to try and see if I can use the affine transformation to describe the relationship between this and this. Between this and this. This and this. Sorry. This and this. You want to see if we can use affine transformation to describe the relationship. If we can use affine to describe their relationship. Okay. So that's what we are going to try. Right? What we are going to try. And the outcome will be interesting for different terrain type. Okay. So this is the but before we dig into the detail, because if I already tell you what it will look like, then it will be boring, a little bit boring. You just need to work on it. Then you are just working on it, and then you don't have any surprise. So I'll be boring for you guys. So and also you guys need to train your skill. Say, okay, if I have some weird result, does it make sense or not? Is it the code is a problem in your code, or is it reasonable result? So you need to have the you can say skill and or the sense to tell that. Okay, so that's why I don't tell you what it should be. Okay, but you already know the enough and necessary information, right, to judge it. Okay. So basically, our purpose over here is, just forget about Corearchy condition equation. If we can, and we'll try to see if we can use affine transformation to describe the object space coordinates x and y and the image space coordinates. Can we use affine to describe their relationship? And for different terrain types. And for different terrain types. So what we are going to do here is, if you are going to use affine, then of course you need to derive the affine coefficients, affine transformation coefficients, those 6 parameters. So in this case, in order to derive that, you need ground control points. So you have the ground control points, and also here is a term that you may not be familiar with, which is the independent checkpoint, the ICP. So what's the difference between the ground control points and independent checkpoints? Actually, in terms of the content, they are exactly the same. Right? In terms of the content, they are exactly the same. So let me, because in the past, some previous students, they usually confuse about what's the differences and what's the relationship, what's the role of GCP and ICP. So let me explain it here. Okay, so in terms of the GCP, basically it means that you have the x and y and the corresponding x and y. Actually, it will be very similar to what we were talking about yesterday. All right, this is your GCP. This is your GCP. So basically, you are going to simulate, or you are going to take, actually, you are going to take some control points with the known object space coordinates x and y, and also the known image space coordinates x and y. Right? You need to have that. And this one, of course, this should be without random errors. Actually, you can do it with or without random errors. That's actually most fun. Okay? So, because supposedly in reality, your image coordinates also have random errors. Also have errors. So yeah, with error. Okay, that's decided now. So this is also with error. So which means that from those object space coordinates, from these object space coordinates and the corresponding image space coordinates, you are going to pick a set of them as ground control points. Right? You are going to pick a set of them as this. And what's ICP? ICP, the content of it is the same. Right? The content of it is exactly the same. Right? So what exactly is the difference between GCP and ICP? GCP is the points that you use to derive the affine transformation coefficients. Right? Again, GCPs, they are the points that you use to derive the affine transformation coefficients. And ICPs, they are the points that you use to evaluate whether you have the good transformation result or not. Okay? The ICPs, they are checkpoints. They are used for evaluation. To evaluate whether you have derived the coordinate transformation that can describe, that can perform well or not. Okay? So, which means that you have a set of GCP. For example, you pick 10. You pick 10 GCPs and to derive a set of affine transformation. And then you have like 100 ICPs scattered around. And then you use, for example, the ICPs could be over here. And you have, for example, here, these points. They are your ICP. And usually, GCP, we will use rectangle to describe it, to represent it, actually. We usually use rectangle to represent GCP. And so circle could be used, circle or crosses will be used to represent ICP. Okay? So, which means that you use those GCPs to derive the coordinate transformation, and after that you have the coefficients, then you can input the ICP point. So after you input the ICP point, for example, if after I input this ICP point, then the answer tells me, the coordinate transformation tells me that the location of that, the precision of this point, after you use the coordinate transformation that you get, then it's over here. It moves to over here. So which means that here, this is the arrow. This is the arrow. And for this point, maybe it moves to here. So this is the arrow. This, maybe here, this is the arrow. This could be the arrow. This could be the arrow. Okay, so what you can do, and some of them are small, some of them are large. Okay, so the ICP is for you to get those arrow vectors. Okay, so these green arrow, they are the arrow vector. Arrow vectors. Right. They are the arrow vectors. Okay? And the arrow vectors actually are the required, you can say, representation in this homework. So you also need to draw the arrow vectors. Why do you need? You can think about why do you need to draw the arrow vectors? Because it actually can show you the systematic arrow. Whether arrow is like large in some area, whether arrow is small in another area, and you can try to analyze. Say, okay, why the arrow is large over there, why the arrow is small over there, and why it has the systematic behavior, or not systematic behavior, or they are all random behavior, random arrows. So you can use arrow vectors to observe that. Okay, so this is a very important way to analyze your arrows. Okay. Alright, this is quite important because usually in the past, many of the previous students, they confused about what's the difference between GCP and ICP and how exactly does the ICP works. So here, any question? Like I said, this is homework, so you need to make sure everything is clear, so that you know how to write a program, how to use those data. Any question? Any part that you are not clear with? Yes.
Is the error vector in the image space coordinate or object space coordinate?
The error vectors. Okay. You will be. We haven't touched that, but you will be in the image space. Yeah, you will be in the image space because we are going to reproject it to the image, right? So you won't be. You are not doing the space intersection. So of course, the fine transformation can help you to to go both ends. You can go from image space to object space or object space to image space. But however, from the you can say from the sake of the context, taking the photo context. So we are reprojecting the object space coordinates to the image space. So in this case, the analysis it should happen in the image space. Because in reality, in this context, you couldn't directly derive the object space coordinate with just one image. You need to perform space intersection. So it doesn't really make sense to perform this kind of analysis in the object space. Okay? So like I said, for the sake of context, for the sake of this photogrammetry context. Okay. Any other? Yes, please.
How many ICPs should be used to verify the transformation?
Actually, the more ICP and more evenly distributed ICPs can help you to observe the error behavior. Yeah, so you can decide the number of it. But however, of course, statistical in a statistics point of view, and if you are finally if you are going to calculate some accuracy index, then in this case, more than 50 is supposedly it needs to be larger than 50 ICPs.
Okay, more than 50.
Okay, any other questions? Right, if not, then let's talk about this part. Actually, this part is what I was explaining yesterday, so it should be easy to understand. So here, you need to simulate, you need to get two sets of points. One is for GCP, and the other one set is for ICP. And then, so you need to pick them from the data you simulated. And then the GCP, it needs to be at least 3 non-collinear GCPs. Of course, that's also what we talked about before. A fine transformation has 6 parameters, so you need at least 3. But however, if those 3 are on the same line, then you don't have enough information for the perpendicular axis. So they need to be non-collinear. So 3 non-collinear GCPs. But of course, you can try to see if they are collinear and what would the error behavior look like. And I encourage you guys to do it because when I was a student over here, I also tried that. I tried to simulate a line of GCPs, and then the error behavior is crazy, right? Supposedly it should be crazy. Right? If it's not crazy, then actually, for some cases, it may not be very crazy. For some cases, but I couldn't tell you what cases is that. Then I will ruin the surprise, right? So I couldn't tell you guys that, but you can try. All right, so formula for the fine transformation is over here. We talked about that already, so I will move on. And this is what we talked about yesterday. So like I said, we have this, we have that on the slide. So this is this. So if you are going to, because if you have more than 3 control points, then how are you going to solve the coefficients? You need to use least squares adjustment. So this is how you can do it. So this is the observation equation that we talked about yesterday, and then this is the equation to solve the unknowns, those coefficients. Okay. So yeah. yeah, that's the case. Okay? So we talk about this, so I don't want to spend enough time to explain it again. So, okay, let's move on. So after that, like I said, you have the coordinate transformation to describe the relationship between these two, the object space x and y and image space x and y, of course with arrow. Then the next thing is you are going to verify whether you have the correct coordinate transformation or not. So one thing is you can reproject ICPs to the image space and then try to see whether it follows the arrow, the normal distribution that we simulated. You can try to see that. Because supposedly, each of them, they have its individual random arrow. So after you project those ICP points, then you can get those amount of arrow and then see if that amount of arrow follow this. Some of them follow this. Just a hint, some of them follow this, some of them they don't, because it's affected by the terrain type. Right? It's affected by the terrain type. Right? So just for you guys to know it, just want you just make sure that you won't freak out if you see like it doesn't follow the normal distribution. Am I doing something wrong? So just FYI, right? Don't freak out. Maybe you are doing the correct thing, it's just because of other reasons that it doesn't follow the normal distribution. Okay. So that's the case. Okay. Any other question? Any question for this part? Alright, if not, then the important thing is the right hand side, but we go over the left hand side first. So when you write a report, actually this is the format of that. You have the title, abstract, keywords,